All right, welcome. Today we are diving into a real classic, a puzzle from a legendary physics book that trips up a lot of students. It's Irodov's problem 1.193. It's all about rotation and tension, and honestly, it all comes down to one key insight. So, let's break it down together.
So before we even get into the nitty-gritty math, let's just think about this intuitively. Picture this. You've got a puck spinning around on a super slick table, so no friction. It's tied to a string that's fed through a little hole in the middle. Now, what do you think happens if you start pulling that string down from under the table, forcing the puck into a tighter and tighter circle? Do you think the tension you'd feel on that string gets stronger, weaker, or does it maybe stay the same? Just get a guess in your head. We're about to figure it out for real.
Okay, so here it is, the official problem statement word for word. We've got a mass m, it starts at a distance r0 with an angular speed of omega naught. And our job, our whole mission, is to come up with a formula for the tension T that works for any distance r as the puck gets pulled in.
First things first, with any physics problem, you've got to deconstruct it. Let's just figure out exactly what they gave us and what they want from us. Getting organized from the get-go is half the battle, I promise.
All right, let's just lay it all out nice and clean. On one side, here's what they gave us: the mass, the starting distance, the starting spin speed, and here's a really important clue. The thread is pulled at a constant velocity. On the other side is our goal. We need to find the tension, not as a single number, but as a function, a formula that depends on the radius r.
Now, a big part of physics is learning to translate the physics speak into plain English, right? So, smooth horizontal plane, that's just a fancy way of saying forget about friction and gravity. Awesome, that makes life way easier. Non-stretchable thread just means the string isn't some weird spring. And constant velocity pull, that's a gem. That tells us the rate the radius is shrinking, dr less dt, is a constant value. Tuck that little fact away. It's going to be a lifesaver later on.
Okay, we've got the lay of the land. Now it's time to choose our weapon. I mean, in mechanics, you've got your big guns. Newton's laws, conservation of energy, conservation of momentum. Which one is the right tool for this specific job?
You know, a super common first instinct here is to jump straight to the law of conservation of energy. And hey, it's an amazing, powerful tool, but we got to be careful. We have to ask ourselves, is the total mechanical energy in this system, the kinetic and potential, actually staying constant?
And the answer is a big fat no. And I'm telling you, this right here, this is the #1 pitfall on this problem. So many people get it wrong right here. Why isn't energy conserved? Well, think about it. You are pulling on the thread. That pull is an outside force, an external force, and it's doing work on the puck. By pulling it in, you're literally adding energy to the system, making it spin faster. So lesson learned, energy conservation is the wrong path here.
So, okay, if energy isn't conserved, what is? And answering that question leads us right to the aha moment. This is the key insight that's going to crack this whole problem wide open. To find what is conserved, we need to think rotationally. And the rotational version of force is something we call torque. You can just think of it as a twist. Torque is what makes something speed up its rotation or slow it down. And it's not just about the force, it's also about where you apply that force relative to the center.
So let's actually look at our setup. The tension force, right, it's pulling the puck straight to the center and the position vector point straight out from the center. They are perfectly aligned. When the force is pointed directly at the axis of rotation, it has zero leverage. It can't cause any twist. So the torque on our puck is zero, absolutely zero.
And that is our golden ticket. Because there's this beautiful fundamental law in physics that says if the net torque on a system is zero, then its angular momentum, we call it L, is conserved. It stays constant. It does not change. For a little object like our puck, angular momentum is just its mass times its radius squared times its angular velocity. And that whole quantity is not going to change no matter how much we pull the string.
Awesome. So let's actually use that fact. We can literally just say the angular momentum at the start has to equal the angular momentum at any other time. So m r0 squared omega naught equals m r squared omega. The mass m is on both sides, so it just cancels out. A little bit of algebra and boom, we can solve for the angular velocity omega at any radius r. And look at that relationship. As r gets smaller, omega has to get bigger. That's the figure skater effect, right there in the math. She pulls her arms in, her r gets smaller, and her spin speed, omega, goes through the roof. Okay, this is huge. We now have a formula that tells us how fast the puck is spinning at any radius. Now we're ready for the final battle. We can go back to the most famous equation in physics,
F equals ma, to find the actual tension force.
Now let's think about the forces acting along the radius, the direction of the string. The only force is the tension. That's it. So that tension force must be what's causing the puck's radial acceleration. It's as simple as that. Tension equals mass times the radial acceleration.
Okay, now the full-blown formula for radial acceleration in polar coordinates, yeah, it can look kind of scary. It has two parts. But remember that little clue we saved, the one I told you to put in your back pocket? Well, it's about to make this whole thing way, way simpler.
The problem told us, right there in the text, that the thread is pulled with a constant velocity. Well, that means dr dt is just some constant number. And what's the derivative of a constant? It's 0. So that whole first term, that ugly-looking second derivative, it just goes away. It's 0. Poof, gone. How great is that?
And just like that, our force equation becomes something you've probably seen 100 times. The tension is just providing the good old centripetal force, mr omega squared. It's the force needed to keep the puck moving in that circle. The coast is clear now. We can see the finish line. We've got all the pieces. We did the hard part. Now it's time to put them together, get our final answer, and, this is the most important part, really understand what that answer is telling us.
Okay, this is the home stretch. We take our nice simple force equation, T equals mr omega squared, and then we take that expression for omega we found just a minute ago, and we plug it right in. We square everything in the brackets, do a little bit of algebra to clean things up, and there it is, our final result. The tension is equal to the mass times the initial angular velocity squared times the initial radius to the fourth power, all divided by the radius cubed.
So let's go all the way back to that first question I asked you. Does the tension get stronger or weaker? Well, this formula screams the answer at us. Look at that r cubed in the denominator. That means as you pull the puck in and r gets smaller, the tension doesn't just go up, it skyrockets. This chart makes it super clear. If you cut the radius in half, the tension goes up by a factor of 8. If you pull it into a quarter of the original radius, the tension is 64 times stronger. That's insane.
And that right there brings it all back to that figure skater. She pulls her arms in to spin faster. We knew that. That's the conservation of angular momentum part. But now we know why it's so incredibly difficult, why it takes immense physical strength. The forces she has to generate to pull her arms in against that rotation go up just as dramatically as the tension in our string. The physics is exactly the same. So that makes you wonder, right? What other things in the real world, or even out in space, work just like this? That's a pretty cool thing to think about.